Let's start with a sorting algorithm called Pigeonhole sort. In our variant, the short-sighted robot is given in advance a palette with all possible colors, only 2 in this example. The list will only contain elements with these 2 colors. The robot picks up the first element and checks which type it is. Every type has its own designated place on the table. The next element belongs to the second type, and so on. Every element is placed in one of the 2 designated spots. The robot is almost done. All it has left to do is put all the elements back. And we got a list sorted by brightness. Let's look again at this sorting algorithm and focus on the dark elements for a minute. We'll mark the leftmost one, and the next one, and so on. Let's see what happens to these arrows as the list is being sorted. The dark elements are still ordered among themselves in the same way they were in the beginning. Also the bright elements, they kept their original order. This is called a stable sort. It doesn't change the order of the elements except where it has to. Insertion sort is also stable. But let's look at quicksort. It has several variants. Most of them, including the one shown here, are not stable. This means they mess up the order of the elements within each group. The list is sorted correctly, but each group has been arbitrarily shuffled. The stability property can sometimes come in handy, as we'll see in a minute. Now here's a stack of small blocks with numbers written on them. We need to build a simple machine that sorts them by the numbers on the left. To help us, we have their binary representation as well. For example, the binary representation of 3 is 0, 1, 1. We have this sorting head capable of reading one binary digit and sorting the block either left or right. Initially, we'll place it on the most significant digit of the binary representation and start sorting. The right stack now contains all the blocks with the most significant digit of 0. These are the smaller numbers. The left stack contains the larger numbers with the most significant digit of 1. The next step is to sort each stack according to the middle digit, again separating it to smaller and larger numbers. And finally, with the least significant digit. Now, we'll collect all the blocks starting with the largest numbers. And we have a sorted stack. So this is a 3-level sorting machine. The sorting algorithm here is called MSD Radix Sort, because we start with the most significant digit. But here is a much simpler design. Counterintuitively, we'll start with the least significant digit and put all the blocks back. We have one sorted digit, but looking at the numbers we need to sort, this didn't seem to have helped us much. Let's now run a second round with the middle digit. Now the middle digit is sorted, but recall the stability property. Within each group, the first digit is still sorted. This is because the blocks in each group kept the order they had before the last round. So we now have 2 digits correctly sorted. A third round will complete the sort. This simple design won't work if we start with the most significant digit. The stack is now primarily sorted by the last round, which sorted the least significant digit, so the numbers are not correctly sorted. Here's a more general demonstration of LSD Radix Sort. We now have numbers written in decimal, using 4 decimal digits. This sorting head is capable of reading these digits. Starting with the least significant one, we'll sort the blocks to 10 stacks and place them back sorted. And now the next digit. The second digit is now sorted. As before, in groups with equal value, the first digit retained its sorted order from the previous round. So we now have 2 fully sorted digits. 2 more rounds will complete this sort. And we're done.